Ahoy, mateys! Let's find the integrated rate law for a first-order reaction. A first-order reaction has the rate proportional to both a rate constant K and the concentration of A, linearly. Rather, the exponent is 1. That's what makes it a first-order reaction. To get the integrated rate law, we are going to need to rewrite rate as the rate of disappearance of A over time. This here is the definition of rate. And again, it's proportional to the rate constant times the concentration of A. Separate your variables is the next step. What that means is I'm going to leave dA on the left and move the concentration of A to the left as well. Notice it was in top, now it's in the denominator because I had to divide both sides by A. And on the other side, I'm going to move my negative, I'm going to leave my K there, and I'm going to move my dt to the right as well. Notice it was in the denominator, now it's in the numerator because we had to multiply both sides by dt in order to get it over there. Now that I'm here, I'm actually literally going to integrate both sides. Get it? Integrated rate law. Let me show you more accurately what I'm going to end up doing. I'm going to integrate 1 over A dA on the left, and I'm going to integrate 1 dt on the left. It's a rule of integrals that you're allowed to move constants outside of it. I'm left with 1 here. The same way if you factor an x out of x, you're left with 1. Anyways, what's the integral of 1 over A, I ask you? You tell me. The answer is ln of A. I ask you what the integral of 1 is, and you tell me it is t. Hey, look, you're right, because you're smart. It goes from 0 to t in both cases. If you're familiar with integration, you're familiar with this notation that I'm using. What that really means is that the ln of A at t minus the ln of A at 0 is equal to negative k t at time t minus t at time 0. Obviously, t is 0 at time 0. Beautiful. Now what I'm going to do is rearrange this for you, just so I can emphasize what exactly is going on. Ln A of t is negative kt multiplying through plus the ln of A naught. What this means is that if I graph ln of A on my y-axis and t on my x-axis, I'm going to end up with a straight line with a slope of negative k and a y-intercept of ln A naught. Let me emphasize what I mean. I put time on my x, and I graph ln of concentration on my y. I'm going to get a straight line. The slope is going to be negative k, and the y-intercept will be at the ln of A naught. How awesome is that? It's the whole reason we do integrated rate laws, is to turn something regular and boring like this into something awesome like this. I want to show you one more thing that only pops out in the first order integrated rate law, and that is I could rearrange this another way to get A of t equals, this marker is crap, A naught e to the minus kt. That's using logarithm rules over here, undoing ln with e to the power of, and then multiplying both sides by A naught. All I want to emphasize here is that A varies exponentially, or rather negative exponentially, or whatever you want to call it, with t. A decays exponentially over time. That's the wording I was looking for. Beautiful. You guys should try doing this on your own. Make sure you understand each step, especially if your teacher actually cares about you doing it. And until then, best of luck to you.